Greetings. Up until now, all problems that I have solved for you were on a single medium. Either it was water or it was air or sometimes R134. Yeah, but still, it was always a single substance. But um, another alternative that we could have is a mixture of gases, mixture of perfect gases. And in fact, air itself is a mixture of different gases, oxygen, nitrogen, argon, and CO2 or other gases which are mixed in air. Now, how do we deal with the mixture of different gases is the subject of this problem. I've selected the problem and the numbers from the book Thermodynamics and Engineering Approach by Yunus Sinja, and I'm also using its table, and I will just not only solve it but explain for you the different intricacies of how to solve problems that concern a combination of different perfect gases. I hope at some later stage I will be able to handle real gas cases for you, but for the time being, we will just concern the combination and the mixture of perfect gases. Well, the problem tells us that there's a cylinder piston arrangement with a spring that basically limits the movement of the piston. The spring behavior is defined in this way. In fact, it's limits of its movement which is defined. It is said that if the volume Vx, the volume inside the cylinder, is zero point 0.1 cubic meters, then the pressure Px is 200 kilopascal. And if the pressure increases to Py equals 1000 kilopascal, then the volume would be Vy equals 1 cubic meters. Okay, so this is how the movement of the piston is defined, and the action of the spring, in fact, it is defined. Now, it says that at the start of the process, let's call it P1. At P1 is 200 kilopascal. Now, of course, we know what V1 would be, 0.1 cubic meter, and temperature T1 equals 10 degrees centigrade. Now, we heat this cylinder, so we add heat to it, and P2 would be 500 kilopascal. Okay, now there is heat transfer, there is work done, there is change of entropy, and as always, we shall solve all different items with this problem, and it would have been very easy if I had said that this is steam or it is air. But here, in this very problem, we are told that whatever there is inside it, it is neon, and that is 25% by pressure. The pressure fraction is 25%. It is O2, which is 50%, and it is N2, which is 25%. These are the pressure fractions. These are the pressure fractions. Which we all know that partial pressures are directly related to mole ratios. So we have mass ratios, mass fractions, and mole fractions. And now pressure fractions directly show what mole fractions tell us. It means that whatever there is inside here, 25% on a molar basis is neon, 50% on a molar basis is O2, and 25% on a molar basis is N2. And now we have to find combined properties of this very combination and use it to solve our problem. Now, the solution to such a problem is just very similar to whatever that we always did. That means that we shall write our equations, decide on our control volume, simplify our equations for this control volume, find properties, draw process and properties on a diagram, and then get everything together towards a final solution. And now, this is what we have to do now for the equations. And the governing equations are here. You see, as before, the change of mass in the controlled volume or inside the system is a function of mass that enters or leaves. The change of energy is the energy going in with the mass that enters, energy leaving with the mass that leaves, heat transfer and work, and the change of entropy within those boundaries is a function of the entropy that enters with the mass that enters, the entropy that leaves with the mass that leaves, heat transfer, and also entropy generation. And what you have to do is to simplify these equations for our very problem. And since there is no mass that enters or leaves, we should write m2 minus m1 equals 0. This is our mass conservation. m2u2 minus m1u1 m2u2 minus m1u1 equals no mass enters or leaves, and therefore it is Q12 minus W12, which is the heat transfer and work. They are both there because when you heat it, it expands and does the work on the spring. And also there is heat transfer, as we know. And then the second law tells us that M2S2 minus M1S1, which is the change of entropy for the mass that is inside this system, equals, there's no mass that enters or leaves, but it is Q12 over Tp, and plus Sgen, which is the generated entropy. Now, a further step we could take with this problem, and it is uh, first, since we know that M2 and M1 are equal, therefore we could just write this uh, energy equation as M times U2 minus U1 equals Q12 minus W12. And for the second law of thermodynamics, what we could do is to assume that all irreversibilities are outside this boundary we have defined. And in fact, since we are assuming that the temperature inside this is uniform, then you could assume that um, the process that happens for this gas mixture inside is reversible. It's not adiabatic, it is reversible, and therefore Sgen is zero. Therefore, the second law would simplify to M times S2 minus S1 equals Q12 over TB. TB is the boundary temperature, is an equivalent for the boundary temperature, and we shall see what's the appropriate value for it during this problem. Well, I've just tried to draw the values for our spring action on a PV diagram. This is P and it is kilopascals, and it is V, and this is cubic meters. Now, we are told that if V is 0.1, then P would be 200, and if P is 1000 kilopascals, then V would be 1 cubic meters. Okay, now we are told that our initial pressure is 200 kilopascal, and therefore 0.1 would be here. And the final pressure, we are told it is 200, 400, 500 kilopascal. So our final point is 500 kilopascal, and therefore our final point would be here, and this would be point 2, where this is P2 and this is V2. And just finding a value for V2 is a simple interpolation. I just do it here. We could write that 500 minus 200, 500 minus 200 divided by 1000 minus 200 equals V2 minus 0.1 divided by 1 minus 0.1. So basically, I have told that on pressure scale, it is 500 minus 200 divided by 1000 minus 200. On volume scale, it is V2 minus 1.1 divided by 1 over 0.1. And the conclusion for V2 is 0.4375 cubic meter. And in fact, to calculate work, we don't need anything more. We don't need to know whatever there is inside this cylinder. And calculating work would be just the area underneath this underneath this curve, underneath this line. And this area is simple to calculate. W12 would equal the average pressure here, which is, I'm just using the equation integral P dV, and I would use average pressure here, which is 500 plus 200 divided by 2, and dV, which is 0.4375 minus zero point 0.1, and the outcome for W12 is 118.125 kilojoule. This is one important conclusion that we have calculated out of, you see, we assumed S tends to be 0. We have now calculated W. Still, the rest of the parameters here are unknown, and in order to calculate them, we need more properties. Why we need properties? Because for U2 minus U1, we would need to write it CV0 times T2 minus T1, and we need CV0 as a property for the mixture. We also, for S2 minus S1, we need CP0 ln2 T2 over T1 minus R ln P2 over P1, and we need R, CP0, and also T. And more important, for mass, we don't know the total mass, but if it is perfect gas, we need, we could write PV equals MRT, and to calculate M, what we need is R for the mixture. So at this stage, what you have to do is to handle the composition of this mixture and see what the equivalent properties would be. Now, the next step for us is to draw a table just like this one and put values, put different gases, neon, oxygen, and nitrogen on different columns, and different properties on different rows. And basically, this would be what we would need for every problem, which there is a mixture of perfect gas as the working fluid. Now, what we have here is molecular mass, R, gas constant for that perfect gas, T critical and P critical, just to make sure that we have a perfect gas, Y, which is the molar ratio, and it is equivalent to the partial pressure of that very component to the mixture pressure, mass fraction, the mass of every individual component, every individual item, number of moles of every item, CP0 of the mixture, CV0 of the components and also the mixture, and also gamma, which is the ratio between CP0 and CV0. These are basically what we need, and the first step we should take is to just go to the tables and see what they can offer us. And there are two tables which are usually in every book you have similar tables, but this one I have selected is you have for different gases, you have molar mass, gas constant, and the critical point properties, temperature, pressure, and specific volume. And as you see for our problem, we have neon in this line, we have oxygen in this line, and we have nitrogen here, and we can just read these values and transfer them to our table. There's also usually another table which for the same gases, neon, nitrogen, oxygen, tells us R, which is the gas constant, Cp, which is the specific heat for constant pressure, Cv, specific heat for constant volume, and K. These are also given us for individual components, and what we shall do is just to transfer these values to our table to have them all together in one place. Now I have just transferred all those data from those tables, those two tables, into this table. This is all we need, and it is the molar mass, R, and TCR, PCR, and CP0, CV0. So we now know everything for our individual gases, and we need some information to see what portion of each do we have. And usually there are two ways to give us. First, on a molar basis. Second, on a mass basis. Now, this is what happens. This is the row that is filled if it is on a molar basis, and this is the row that they would fill if they give us on a mass basis. This problem tells us about partial pressures, and therefore it gives us on a molar basis, and it tells us that we have 0.25% on a molar basis of neon. We have 0.50 of oxygen and 0.25 of nitrogen, and the sum would be 1. So once we have such data on a molar basis, then we could immediately move to the molar part of the story and calculate the molar equivalent molar mass. And the molar mass of the mixture M of N equals sigma yi and mi. Basically, we have to multiply each molar mass to its molar portion of it. So the equation would be 0.25 times 20.183 plus 0.5 times 31.999 plus 0.25 times 28.013, and the equivalent molar mass of the mixture would be 28.0485. kilojoule, kilogram per kilomole. And that's what I would write here, 28.0485. That's a very important step we have taken. We have now, from this value, we have found one equivalent value for our mixture. Now, there is a very, very key equation which basically transfers everything from molar basis to a mass basis. And the equation gives us the mass fraction for individual items. It is this one. It is MFI, which is the mass fraction of component I, equals Yi, which is its molar ratio, times Mi divided by M. What does this equation do for us? I think if we write it on a dimensional basis, it would be very useful. Mass fraction is kilogram of I divided by kilogram of mixture equals Yi, which is kilomole of I divided by kilomole of mixture, multiplied by Mi, which is kilogram of I divided by kilomole of I, and an equivalent molar mass, which is kilogram of M divided by kilomole of M. What does it do for us? You see, these kilomole of I and kilomole of M cancel with these two ones, and all we are left is kilogram of I by kilogram of M. And therefore, a molar fraction would change to a mass fraction. And therefore, we can just fill in this row, which is important to us. This row would be 0.18, 0.57, and 0.25. And the sum would be still 1. Let's just put numbers in this one to make sure that we are doing right. You see, MF, say for neon, would equal Y neon, which is 0.25, times M, which is 20.183, and divided by the equivalent molar mass, which is 28.0485. And the outcome for this one should be 0.18. This is how we calculate different values in this row. And once we have mass fraction, then we could extend this value, because all these rows are on a mass basis. We could just extend it to calculate CP0 and CV0. I shall do it in my next video and tell you in detail how the rest of this table is filled and how we solve the rest of this problem. Cheers.